Welcome to the Bytecode. I'm Rosh Shafu, and today's episode is with Harry, who's gonna walk us through the visitor pattern and how it's implemented inside the Solidity compiler. Harry, thanks for taking the time, man.
Amazing. Um, so, so maybe I can start with like a 30-second introduction about myself and then what I'm going to talk about. So my name is Hari. I used to help build the sort of decompiler at the Ethereum Foundation in the past, and then now I work at Spirit, for the last 2 or 3 years, where we do some cool security stuff. And for today, I wanted to share this idea of a visitor pattern. It's a very common concept in building compilers. And if you understand what the visitor pattern is, that will allow you to build a lot of cool stuff that has to do with programming languages. And I will share some examples of the cool stuff that you can build later if you want to give it a try. But the goal of goal of this is to really help you understand one concept and then show you how it's used in the sort of decompiler, and then also show you some way to like hack around this idea. And then I can tell you some examples of cool things you can build once you understand this concept. I want to start by prefacing that this is a very non-trivial idea. And the only way to truly understand this is by actually building something using this concept and like hacking around and seeing it for yourself. Just talking and like understanding wouldn't really cut it. But then that's kind of fine. I had to like really hack around it to understand what it meant for the first time. And that's also why this is such a powerful concept that you see all the time in compiler implementations. Okay, so this is the Wikipedia for visitor pattern. It's like super broad. Like I don't think it really tells you what it is. As I said, you kind of have to hack around to understand what it is. You can see all this, complicated diagrams. It almost seems like it's from a meme with, people trying to draw all these arrows.
Yeah,
But
Harry,
it's
can you
actually, yeah.
maybe zoom in just a little bit?
Okay. Does that help? Should I
Awesome.
keep going?
Perfect.
Yeah. So this is like the Wikipedia understanding of the visitor pattern. It looks very complicated, and it's not that complicated. But it's it's one of a very powerful pattern. Okay. So I will start by showing you a Rust implementation of the Solidity abstract syntax tree that I wrote. It's very, very like granular. It's like very condensed. And this is something that's like easy to understand if somebody wants to start. I will get to the C++ version of it soon. I know C++ has a reputation for being a difficult language for a lot of people. So that's why I also wanted to put this Rust version for people to like have a look at. I will also compare this implementations a little bit, and you can see the differences between some language choices in C++ versus in Rust. Okay. Okay. So let's start with what can we actually do with the visitor pattern once we implement it. And I have this example here of what you can do with it once you implement it. Okay. And then we will get to how we actually implement it, in a bit. Okay. So the goal of this function is you have the source code of a Solidity smart contract, and you want to extract all the functions that are defined in this Solidity contract. Okay. If I tell a random person to do this, they would often tell me, okay, I can write a regular expression to do that. I can write a regular expression where, there's function, the name, something like that. And it almost always works. But it doesn't truly understand the syntax of the program. And I can almost always provide you with a source code where it will either parse it incorrectly or it will parse some additional things. For example, I may be able to write a function f inside a comment, and your regular expression may not be able to understand that this is a function that's defined inside a comment, and therefore it's actually not syntactically inside this this program. So regular expressions, broadly speaking, are not um, powerful enough to understand source code. It's usually a good and fast way to do some tricks, but it's never enough. You almost always need to build a parser that is like significantly more powerful. If you have some understanding or background in some theoretical computer science, there is this concept of grammars. There is this concept of like different types of grammars, and you will understand what kind of grammars regular expressions can actually parse at a theoretical level. We don't have to get there today, but broadly speaking, regular expressions, they are pretty good at basic stuff. But as soon as we're talking about programming languages, it's very limiting. So you need to do something that would parse the source code, and then you need to find a way to extract details out of this parsed syntax tree. Okay. The first thing we will try to understand is what is an abstract syntax tree. Let me pull up an example of the AST documentation that I believe the hard hat team made. Okay. So this is Solidity AST.netlify.app, and this will give you all the things that are involved in building the abstract syntax tree. And I will show you right now how it actually looks like. It's JSON representation. Let me try to find one of the tests here. And I have so this is how the Solidity abstract syntax tree for the counter.js, counter.sol looks like. Everyone's favorite smart contract. It just increments a counter. So it starts with a bunch of, if you understand what a tree data structure is, it's a tree at the end of the day. It starts with the first node, which is the pragma directive. It tells, and this is like the parsed version of the pragma directive. It tells you Solidity, the symbol, throw 8.13, and it was able to correctly parse that this is a pragma directive. And there is a contract here. There's a contract, there's a type of the node called contract definition, and this contract has even like more subnodes or like children's that are other things. The variable is a variable. There is a function definition. There is a block. There is other things over there, and each of these nodes they are like listed over here. As an example, an event definition is a node. A struct definition is a node. A lot of the UL statements are a node. There is a node called statement, which can be one of these things. It's a what is it called? Like a like a enum of these types. So any questions so far, Shafo? I think I've started off with like a very complicated concept.
Uh, no, so good so far. Interesting website. First of all. Never seen this website before. Uh, but yeah, maybe it would be helpful like a two-line description of what the visitor pattern is actually is exactly before we go into more details.
Yes, I mean I will get there because
Okay.
you have to understand what the abstract syntax tree is to get to the visitor pattern. Um,
Okay.
but to really summarize the visitor pattern, so it's a way to visit the nodes of this abstract syntax tree, and most of the time when you have a tree, you talk about depth first search, breadth first search. Depth first search being like you visit a node and then you visit its children and then you visit its children again, and then you try to traverse the entire tree by doing this, going to the children first. The breadth first search is where you start at the node, you try to visit each children one by one, and then you traverse the children of the children one by one, and that's like two examples of a tree traversal algorithm. And the visitor pattern is almost like a depth first search, but you do it twice. So you try to visit each of the children of the node, but you also like do a visit backwards. So it's not really like a depth first search or a breadth first search, but it's like a pattern where you go to each node, and then there is a way to go to the child nodes one by one, and there is a way to like traverse backwards. So this is what makes it like kind of powerful. Like you
Mm.
visit the tree two times, one forward and one like backwards. And then using this pattern, you can build a lot of complicated things. Um, I would say the first complicated thing you can build is a diagnostic step. You can diagnostic is anything where you try to find a pattern in a source code, and then you can do something about it. In a compiler, this would be something like an error message saying that okay, there is something wrong with the syntax, there is something wrong with the types. Let me quickly show you how it looks like in uh, type checker. This is type checker.
Okay. You could also
This is
use it for optimizations, for example.
Yes, this is a very powerful concept. Once you understand how to traverse the tree, there is this concept can be applied in many different ways. And at the end of the talk, I will give a challenge to people that they can try. They can try to write a compiler from Solidity to Dot. Dot is a simple programming language for drawing graphs, and you can use
Mhm.
the visitor pattern to compile Solidity code to Dot, and then try to draw a graph of the source code. So it's a very fun and simple compiler you can build using the
Mhm.
concept you learned today. Okay, um, let's quickly see how type checking would look like in the compiler using the visitor pattern. Um,
So right now we're in the Solidity compiler, C++
yes,
implementation.
exactly. What is a symbol? Yeah, so this is a visit node of a function definition type. And this is how a type checking would work. So you go to the function definition, and then you check if it's marked virtual. And then you can do more analytics. You can check if it's a free function. And then, you have this new error saying, okay, free functions cannot be virtual, and that's an error. And it will almost always stop compiling after those checks, and then tell the user to fix it. Um, and using the visitor pattern, you were able to simplify this type check to a single function. All you have to do is, define a visit, and then the type that you want to visit. This is function definition, and then assuming that you have all these annotations ready, and the annotations are there by doing the visits over and over again. And then once we have these annotations that, okay, this function is actually marked virtual, this function is actually marked free, you can do a lot of diagnostics. You can tell that, okay, these combinations cannot work together, and you can tell the user to fix a semantic or syntactic error. Does that make sense? That's okay. It's a very quick example of an error message and how to do it.
Yeah, maybe one weird question. What is a free function in this context? What does it
Oh,
mean it's free?
the free function is so in Solidity you can have functions inside the contract, and then you can also have functions in the source unit. So there is no contract; it's just a free function. So there is no contract
Okay,
attached to this function.
I see.
So it's a replacement for internal functions, so to speak. So you can
Mhm.
have a source unit. I mean, it's a source code. I mean, sorry. I mean, I talk a lot in the notation of the AST, but I will try to simplify it. So you have a file, contract.sol, and then you just define a function. No contracts. You can define a function f or function add, and then it takes two numbers as inputs, and then you return a number. So this is a free function. It doesn't have a contract or a library attached to it. This is a somewhat recent addition and wasn't in Solidity for a while. I think it was added in like somewhere in Solidity. I may be wrong, but it's a pretty recent thing. So even if you skip the free function, you can see a function is virtual, and if it's a constructor, you tell an error they're saying that okay, constructors cannot be virtual. What is a different one? Let's see. Okay, a function is virtual and it's actually a private function, and then you tell them okay, virtual and private, it doesn't make sense together. A different one is it's virtual and library, and then you tell the user that a library function cannot be virtual. So these are like very simple way to do diagnostics, and once we have the visitors implemented, it's a matter of just defining a single function and then doing this diagnostic step. Let me just go back to the other example here and show you how it looks so similar. So this is my Rust version of the Solidity AST. Just like that here, you have a single function, and then you can like store all the names of the functions by visiting the function definition node and then extracting the name of the function. Let's actually look for that doesn't work, but I can look it up here. I can show you how function definition is defined. Where is it? Functions. Yeah, there you go. Function definition has all this, all this like struct members. It has, it has a node ID that is across every single AST element. It has probably has I think it's a name. It has the visibility. This could be public, private. It has this concept of virtual. It has this concept of scope, which is, if it's inside a contract scope. It has the concept of return parameters, and so on and so forth. Maybe I started with like a very complicated struct to show with. Let me see if I can show variables. Okay, variables. Variables are a simpler concept, I hope. Yeah, even that is a little bit complicated because there is the idea of whether the variable is constant. There's the idea that whether the variable has all this override. In the context of a contract, you can say that this variable overrides a different function. There is this concept of whether this variable is a state variable or not. Okay, does that make sense, or did I get too complicated right away? Shafu, can you hear me? Oh no.
I was muted. Yeah.
Oh,
I was muted. Sorry. Yeah, I was saying maybe it would make sense to take one step backward, just to clarify some things. So the first thing is, a compiler, in this case, a Solidity compiler takes Solidity code and returns EVM bytecode, right? An
yes,
AST is something in the middle, right? Between your Solidity code and your EVM bytecode, and an AST makes it very easy to do the things you already mentioned, diagnostics, optimizations, and stuff like that. The repository you're showing right now uh, as I understand, is something it's a Rust implementation of the AST where you already need the AST. You need to load in the AST basically. There's not a compiler written in Rust. This is just the AST bindings.
exactly.
Uh, okay. And okay, one interesting question I would have is uh, why exactly did you write this? It just makes it easier to do some things in Rust?
Yeah, it's a good question. I mean, the real story of me writing this is I was trying to hack something at a hackathon, and I wanted to build in Rust, and I knew how to write it in C++, and I couldn't really find a good implementation of the Solidity AST in Rust. And then, this hackathon was, over like 2 days or something, and I couldn't like rewrite the whole thing, and then also build something of it. So eventually, the next week or something, I started working on this, the Rust bindings to the Solidity AST, so I can like keep hacking it in an easy way. But I can just show you how it looks like in the C++ implementation. It's almost exactly the same. Um, you define, so everything that's over here, all this node has an equivalent struct variable, struct or class over here. So there is a class called declaration, and then there are some functions that can help you with stuff. For example, it can tell you if it's a public, internal, private, external, and we have this assert which will which is something interesting on its own. I will get to it later. But the too long didn't read of what a compiler does is you start with source code, which you can imagine it's like strings, and then the first step is going to be parsing. So let me go into the parser. Okay. So the goal of the parser is to convert all the strings into what are nodes in this abstract syntax tree. So it tries to use some parsing algorithm. Parsing algorithms are a rabbit hole, and it tries to use one of the parsing algorithm that's very similar to the V8. The V8 is a JavaScript engine that's used by Chrome and others. As you know, like Solidity had a bit of a deep inspiration from JavaScript early on, and the parser has a lot of similarity with the V8 parser that pretty much you and I are using right now to communicate with each other. So that's some like fun history about Solidity parser. So it's very similar to how the V8 parser for JavaScript is implemented. And the first step in compiling is you have to understand the source code and convert that into like a data structure that's like a tree. And we call that abstract syntax tree. And the syntax tree often has very minimal annotations. So when I talk about annotations, you see that these nodes are very rich. These nodes have all these things like, okay, the body, condition, documentation, all this stuff. There are very few things that you can understand just from parsing itself, and the parser will try to do its best to annotate as many elements as possible. And in the following stages, you go through this abstract syntax tree multiple times, and then try to annotate more and more details into each of the nodes. And these details are later used for more things. For example, you already saw in the type checker that it was using details like whether the function is free, it was using details like whether this function is virtual, and trying to pattern match all these things. So yeah, that's like how the compiler works broadly. And after several rounds of going through this abstract syntax tree, you get to a point where you have a program that is actually valid, and it's time to generate bytecode for this Solidity program that you just parsed and did a lot of diagnostics on. And this is the phase called code generation. And code generation is this idea where you convert this abstract syntax tree into like actual bytecode. It's not as simple as that, because converting to bytecode also involves several steps and several translation layers in between. And one of the translation layer is going to be converting the Solidity AST to UL sort of AST. So what happens is that each of the Solidity lines get converted into something that is equivalent and semantically equivalent in UL. And then finally, you have this UL program that you can generate bytecode out of. So effectively, a compiler, what it does is you try to convert all this text into a tree, and then you just keep translating this tree one after the other. And then at the end of the day, you get a tree that can be outputted into a bytecode or something else. And that's why the challenge I told you at the end, I mean, that I'll tell you at the end about converting from Solidity to Dot is it's a very fun exercise to go through. So yeah, do you have any questions right away?
No, that makes that's a great overview. Well, maybe one last thing is to add. You don't like on a theoretical level, you don't necessarily need to generate an AST, right? It just makes it a lot easier in generating EVM bytecode in the end, or in general, like generating bytecode in the end.
I mean, you pretty much any modern compiler, you have to
Yes.
go through the same type of code generation. There's a lot of innovations in how people do it, and there's a lot of magic in various compilers. But it's almost impossible. Well, unless the language you're working with is like very simple, it's almost impossible to just straight away parse and generate bytecode like immediately. You have to go through this phase where you have to go through the AST multiple times, like several times, to keep annotating more and more details, and then doing diagnostics, doing this translation to probably an intermediate language. That in Solidity's case, that is Yule, and then doing optimizations on the intermediate language, and then finally you convert the intermediate language into EVM bytecode. So this concept of starting with a string, converting it into a tree, and then doing maybe hundreds of transformations on this tree, and eventually getting a bytecode output from the tree. That's like very common in every compiler.
Yeah, definitely. One question I have is I've never looked at the Solidity compiler before, but why the AST to Yule step and not AST to code generation directly? Why the Yule in the middle?
I mean, that's a very good question, and it's also very it's also a very deep question to answer. So Solidity actually, I mean, I kind of lied. There's actually two different ways to convert from the Solidity AST to the bytecode. And in the past and in the very first implementation of the Solidity compiler, it actually generated the bytecode directly. And when I'm talking about bytecode, I'm talking about like an assembly representation of the bytecode. It's still like very rich. I can
Mhm.
probably go into it. It's called ASM not this one. Let's see. Um, EVM. Hmm, it's been a while since I worked on Solidity, but yeah, abstract assembly. That is what we call um, that's like the output of um, that's like the final output you get. And then once we have the abstract assembly, it's very simple. It just has it has some like labels. It has some jump destinations. It has symbolic jumps, so you're not like jumping to a number, but rather you're jumping to a symbol. And then finally, there is an assembler step that would convert this abstract assembly into actual like bytecode. So that's where you actually get the binary, or everything gets converted into just pure raw data. Um, but this is an abstract representation of it where all the jump destination are symbols. So instead of jump to 0x 50, it will be jump to tag 20, and tag 20 is a name. And then you can put the bytecode line by line, and then you can run an assembler which would convert this syntactical representation of bytecode into actual like raw binary data. But that's pretty much how most compilers work. If you use like C++, you would know like an assembler step and all these things. But back to the original question, the original implementation of Solidity went from AST directly to the bytecode, using this abstract assembly or assembling step. But you quickly learn that this is actually quite complicated and it doesn't allow you to do certain things that you want to do. For example, if you want to write really powerful optimization steps, this data is not enough. Like this data is like very simple. Like it has things like what an instruction is, what a jump destination is. That's about it. It doesn't have a lot of information on like control flow. It doesn't know if this is an if statement. It doesn't know that this came from a for loop, or it doesn't know it came from a function jump. Everything is just jump. It doesn't know if it's an if. It doesn't know if it's a function jump. It doesn't know if it's a for loop jump. So if you want to optimize this, you need to like magically extract all this data and then try to like build optimization step. That gets very complicated. And secondly, the other problem is this gets way too low level quite quickly, which is not a problem, but it also adds a lot of complexity in the code generation step of the compiler. And complexity often means it's easier to build and it's easier to have bugs. And you almost always want to go through an intermediate language and then do a final compilation to this abstract assembly, um, and then going into the bytecode rather than like directly going to the abstract assembly to bytecode. So two reasons. One, it greatly simplifies the code gen. It's much easier to work with an intermediate language and take it from there than to directly try to go to this abstract assembly step. Um, I can try to see and show you an example of how CPP statement compiler utils. This is going to be some helper functions to work with stuff. So this is how the AST to abstract assembly works. This is an example of how some bytecode is generated. This is a function called allocate memory. So you first fetch free memory. Let's see if I can find this. Okay, so fetching free memory pointer. So it appends you this type called free memory pointer and then does malloc. This is as you mentioned, this is how you go from like AST directly to the bytecode. You just keep pushing instructions down to the stack. And then it does the swap, it does this dupe, and it does this that. It's very complicated, and it quickly gets really complicated to work with the code. You can already see this is annoying to read. Like swap, dupe, add. You don't want to work with this, and it quickly gets complicated, and this can be a source of a lot of bugs if you're not being careful here. This is not even the most complicated routines. When I was building the compiler, I had to do a lot of debugging and at some of this very complicated routine, and it was very fun tracking these bugs. I really enjoy like finding what these bugs are, and I really enjoy working with debuggers and tracking down bugs. But it's an extremely painful process to work as an engineer, and yeah, it doesn't really scale that well. And I can show you how the similar thing works in Yule, and you can see the difference day and night. Okay, I'll take I'll duplicate this tab and show you Yule utils. Okay, you can see how it looks similarly for Yule. What was the function we were using? Okay, allocate memory. Let's see. Allocate memory. Is there a function like that? No. But I can probably do a mload. Mload. Yeah. Yeah. So you can see the alternative using the IR, which is a template like, okay, it allocates memory by returning this symbol called memory pointer, and it does an mload of the free memory pointer. And the free memory pointer is, defined somewhere over here. It's like sort of like 60 or something like that. I forgot, but it doesn't matter. It's just a number that has to be reasonably big to begin with. So look at the difference between this versus something like this or something like this. You don't have
Mhm.
to deal with any of the swaps, any of the dupe. Like you have a very clean, somewhat clean like language, and you just have to build these templates and glue them together. So does that make sense?
Interesting. Interesting. That's really interesting. Like I, the templating is it, but isn't it a bit annoying to work with the templating stuff?
Sorry, can you repeat that? I missed you for the last 30 seconds.
Yeah, my question was, isn't it a bit like this super interesting to see like the templating? My question was,
Hmm.
isn't it a bit annoying to work with it? Like I always
Oh,
feel like it's a bit weird to have like a big string inside your, you know, if that makes sense.
that's a really good question, and I think this is a bit of a limitation of C++. So if you look at the fee code base, you can have some high-level constructs. So if you look at the equivalent in some Rust, so Rust has this very powerful macro system, and you can kind of rewrite this using a macro. So it's like a lot of like macro magic, but you can have somewhat high level way to write the same thing. If you have a more powerful like meta programming or like macro system like in Rust, you could probably get something similar done in C++ as well. But we decided to take the simple way where it's a string and it's like a bunch of templates. And we use this templating language called Whiskers. Let me pull up a link for Whiskers. It's a very common template. Whiskers. It's a very common templating language. No, it's called a mustache, I think. Yeah, it's one of those. What Whisker? No, mustache templating. Yeah, there we go. Let's pull it up here. So this is a templating system that has, it's cross-platform or like cross-language. So you can use a similar syntax like this and build templates, and you can generate code. Um, I'm pretty sure this is quite popular for building websites, and you have to do a lot of templates. But even in programming languages, templating is quite useful, as you can see here. Um, but yeah, it's a very good question, and you can see how this is so much easier to work with as opposed to like all the swaps, dupe, add, dupe one, add, like God knows, this is not even some of the most complicated piece. The array stuff. Okay, I want to show you some array stuff. This is yeah. Now things are getting quite complicated. This is what is this? What does this do? Let me see. So this tries to do some encoding, and it tries to like you have to leave all these comments about how the stack would look like. You have to do all this for loops where you have to do all this dupes. You have to do all this add. And a lot of times this is not even the most optimal way to do it. There are several places where you can keep improving how these are allocated. But it's a huge mess, and it's a good way to start writing a compiler, but this is not a way to maintain a compiler. And we had the legacy phase, and I'm happy that we're kind of moving away from that.
Interesting. Very interesting. Yeah. Okay. One other question I have is, um, so so something like Viper, right? Are we sharing any compiler infrastructure between different EVM language, or is it a completely different stack? And another question would be, uh, something like LLVM, right? Which a lot of programming languages use. Is anyone working on a EVM backend for LLVM?
I mean, this is a great question. Let me pull up something. Like, I get this question all the time. Like, is there an EVM LLVM implementation? Why is nobody doing that? Must be
Yeah.
great, because you get all this optimizer stuff. So this is an EVM LLVM implementation from the Ethereum Classic. So for those of you who don't know, Ethereum Classic is a fork of Ethereum without the DAO hack. So after the DAO hack, Ethereum decided to fork, removing the DAO hacker from doing their exploit. But the Ethereum Classic were the purists. They said, okay, code is low, and we have to stay on the original chain. So this is a different Ethereum folks, and they had this idea of EVM LLVM implementation. People spend a lot of time on this, but I don't believe there is any concrete thing that you can use from here. And the reason is that LLVM is designed for like um, register-based backends, and not really like the stack-based VM like EVM. So you're already working with something that's a bit hacky and wasn't designed for EVM. Um, I know people get around this by saying that the number of registers in the machine is zero. They will put a configuration, but LLVM wasn't designed for this use case. And all of a sudden, like you're trying to retrofit something it wasn't designed for, and it just gets very hard to work with. LLVM was also extremely complex, and you're now trying to hack around something complex to
Mm.
something that it wasn't designed for. So there were attempts. There were many people who tried LLVM, EVM in different flavors, and this is one of the popular ones. But I don't believe they have a concrete tool that you can use right now. One successful implementation I would say is from CK Sync. They use LLVM quite a bit. I don't fully understand the details, but they do translate Solidity or Yule into an LLVM backend,
Mm.
which in turn gets translated to like a ZK, SCK programming IR that they build, if I understand correctly. So the CK sync work is the closest to an LLVM EVM translator that exists today. But even then, they have an entirely different use case. They wanted to support like CK or zero knowledge proving for these smart contracts instead of trying to generate EVM bytecode at the end of the day. So yeah, long story short, a lot of people tried. I'm yet to see an implementation that is like easily usable. Um, and long story, and I wish there was very shared infra that can be used across compilers. Yule somewhat was designed for it. So Yule has a couple of design goals. One of the design goals is like we want Yule to be very simple. Um, and this is like a broad philosophical point that I always found quite fascinating. So Solidity is designed to be extremely simple. Like you know how to code, like you can kind of write Solidity smart contracts, and that's both good and bad. It's good in the sense that anyone can now deploy smart contracts with like a few lines of code, but it's also bad in some other way because you're dealing with money and you really want people to put a lot of thought into their programs, and Solidity might look like it's way too easy to write this stuff, and it's actually not that easy to write a safe piece of code. And the other thing I always found fascinating about some of the design decisions behind Solidity is it exposes a lot of low-level stuff to an average developer. So Solidity exposes this idea of ABI a lot. So the ABI means
Mm.
application binary interface. It's how the binary, it's like a binary format, and standardizing how code and calling conventions are defined in the binary. And in 99% of programming languages, you never even have to think about this concept of ABI. In C++, you don't have to think about
Mm.
ABI. In Rust, you don't have to think about ABI. But it's a very important concept for building compilers and building shareable binaries. But almost every Solidity engineer knows this concept of ABI. So I always found it fascinating how much low-level details like Solidity exposes you, despite it being a very easy to use language.
Mm.
So I don't know how it happened, but it happened. And I also find it fascinating how many Solidity engineers can also write assembly. Like a Yule is a very simple assembly language, and I would say like 50% of Solidity engineers can write some level of assembly, and that's not true in any other programming language. Like you can see a lot of hardcore assembly in like C programmers or C++ programmers when they have to do high performance computing. But beyond
Mm.
that, it's almost impossible to see in other high level languages to see people writing assembly inside the high level language. So Solidity is like a very contradictory language. Like it's very easy, but it also exposes a lot of crazy stuff. And I'm very surprised how many people understands concept like ABI assembly, which in most other languages you never have to understand this.
Interesting. Very interesting. Obviously, obviously, writing smart contract has this interesting context of gas and so on and so forth, of optimizations, um, which I think is the main point of using assembly. But do you think like every time someone uses assembly, it's basically the fault of the compiler because the compiler isn't good enough?
I mean, this is a great question, and I think the answer is like yes and no. Um, I'm saying yes and no because there is always something you can do more as a compiler to optimize the code. But having worked on the optimizer for a while, there are certain things like if you give me a challenge, if you give somebody a challenge and ask them to make the most optimal piece of code for something non-trivial, you can almost never beat the assembly implementation of it. Like
Mm.
it doesn't matter if it's like EVM, it doesn't matter if it's like x86 or some other machine. If you understand how to write assembly, you can 100% of the time beat whatever high level language you're working with. This is something I've learned while building an optimizer. Like there is always more you can do, and it's never enough in any language. Um, but a lot of like systems like LLVM or GCC, they try to manage, they try to squeeze a lot of things, and you still get quite a bit out of your system. But if you really want to write high performance software, like understanding assembly, that is gonna take a long way. So the answer to that question is like it depends. Like the compiler should always be able to do more, but there is a limit to what compilers can do, and a human can 100% of the time beat compilers if they really want to squeeze performance. But it's a matter of, is it worth it? Is it worth putting all this work
Mm.
for to get like 5% improvements? And a lot of times the answer is no, but when you really have to do it, you can beat it. And this is, I have a bit of a background in building optimization software for math. So it was building
Mm.
solvers, linear algebra solvers. Um, and performance is very important here. And I mean, it's quite popular lately because of AI and all these linear algebra implementations in Python and all.
Mm.
But even in the Python implementation, it's just like a wrapper around like this, the implementation in C, and
Yeah.
like and this is like a rabbit hole. Like you wanna write faster and faster matrix multiplication, matrix algorithms. You wanna write fast. If you wanna write fast algorithms, you have to now go to C. And if you want to make it even
Yeah.
faster, now you have to go to assembly. If you want to make it even faster, now you write it in like some hardware accelerated system, like
It
QDAV
sucks.
or yeah.
It sucks.
It's just like you can always go deeper and deeper. And then if you want to go even faster than CUDA, now there's like ASIC chips. You can build custom hardware. You can create new instructions. So performance is like a rabbit hole. Like you can,
Mhm.
it's almost there's like levels you can go deep, and it's a matter of like trade-offs. Is it worth, building a new chip to make your software run faster? And if you're building AGI, maybe it is. And yeah, it's a fun rabbit hole to get into.
Yeah. Oh, that's interesting. So I have a machine learning background. So yeah, the Python thing is just, the wrapper is so thin, and once you get to the C++ or the C part, your basic tools don't work anymore, and you cannot do anything. So at least in Solidity, it's like a built-in feature to the language. Uh, but what I found interesting is when you said like you think 50% of all Solidity devs have a basic understanding, can basically write some basic assembly. Um, I don't think this will ever go away. I just think this number will drop, right? Because, like in my opinion, if we scale things and layer twos, layer threes, or whatever, like there will be one point where okay, you deploy the stablecoin on layer two, and gas is just not an issue, right? You just don't care. But you're on layer one, you write some very important infrastructure that's gonna be called like a million times, you're gonna drop down to even assembly. I think this would like what we're gonna see.
Yeah, I think you're 100% right. I think L2s make this art of optimization like moot. And I want to share one article again here. This is called Lost Art of Struct Packing. So if you if you ever wrote C in the past, or like studied C, one thing you learn in C is this idea of packing structures to optimize for like memory. And the same thing happens in like Solidity as well. And these concepts are like evergreen in some sense. So the idea is that, okay, you define a struct, you have like, all these different variables. What is the right way to put the variables in the struct? And depending on how you order it, you can save sometimes space. And this is a common thing in C and optimizing in C. And I think this is a very fun article if you want to read about
Mhm.
how to optimize structures in C. And it's exactly the same thing as packing structures in Solidity. It's like a evergreen concept of optimization. And what happened eventually is that computers become faster and faster, and optimizing this didn't really matter. But there is also this saying that computers have become like faster, like almost beating Moore's law. But then the software has become slower. So I don't know. I don't know how to how to think about it in the end. People don't have to deal with it, but you definitely see that software has become slower. The average app today is like some Electron app with all this app wrappers, and takes so much RAM. And I don't know if it's any better. Um, yeah, it's a complicated discussion.
Interesting. Yeah, it's interesting that you brought up the structure alignment thing. Recently I watched this video. I'm gonna link it in the description down below. It's a patch to the Linux kernel that I don't know
Yes,
improved the speed. Did you see this?
yes, I saw that.
It's like a forty
Yeah, I
percent
saw that. Yeah,
improvement to the
yeah. I mean,
to some TCP thing or something, and it's
yeah,
basically like they switched around two variables. That's it.
exactly, exactly. So
It's
this is
insane.
what I said. Like, if you really know what you're doing, you can beat every single compiler out there. So the magic of humans are it's like unbeatable today.
Yeah, yeah, yeah.
And one
Nice
other,
man.
I mean, on the topic of structure packing, people ask, okay, why can't the compiler figure out what is the actual best ordering? Because a human can figure it out. And the problem here is that, again, this is a classic problem in mathematics, like how to pack objects. And this is if I remember correctly, it's at least NP hard. So which means that
Mm,
intractable to, not intractable, but it's very hard. It's very computationally hard to compute what is the optimal struct padding. So you cannot really put routines into the compiler that takes like exponential number of steps, or even beyond. The compiler has to run quickly, and you cannot have unbounded things like an exponential algorithm into it. So it's always a bit of a challenge. You can build heuristics to make your struct packing better, but the optimal one, it's a difficult problem. Um, even mathematically. So you cannot really build it into the compiler. You can build some heuristics to run this over like few iterations and see what you get out of it. But then the trade-off is that now the concept of ABI is complicated. Okay, what I'm trying to say is that when you define something like, okay, the character P, character C, this array of character for pad, and then a short variable in a C struct. And if you rearrange this, they have different ABIs. Now the way to call them in the binary is different. So this is the other struggle and other trade-off you have to make. And C and C++ often have very strict notions of ABI, whereas other languages like Rust, they have a somewhat loose notion of ABI. So they don't really expect a lot of backwards compatibility or being able to call from a external program to the same binary. So it's a very challenging trade-off space. Do you want to have standards on how the binary would look like, and then you cannot really do all this fancy optimization, or do you want to have like more performance, but then you have to lose some standards on how the binary would look like. So
mm.
a lot of trade-offs to make, and the compiler have to make one trade-off or the other. And this is again why a human can sometimes, not sometimes, almost always beat any compiler if they really want to try.
Listen, man, I could go for hours talking about this, but we're nearly at 1 hour. Should we maybe finish by talking about your dog challenge?
Yes. Okay. I mean, I
Okay.
will I will spend like 5 minutes explaining the visitor pattern. So there are two different data structures. One is the nodes of the abstraction index tree. You can see nodes like block. You can see nodes like what did we go with the? You can see other nodes over here, and every single node has to implement this function called accept. And the goal of the accept function is to take a visitor. I'll explain what a visitor is later. The node is going to take a visitor, and it defines how to visit the children. So with a block has is a vector of statements. It tells you that you take the visitor, and now you visit each of the statements those are the children. And at the end of the day, I mean, at the end of all the visiting, you call this function called nVisit, and this is how the two different like visiting forward and backwards work. And let's now go into the visitor and see how a visitor is implemented. There we go. So a visitor in the Rust sends as a trait, which has a lot of these functions. It tells you, it defines all these structs, and it has two different functions for each node. And it is a generic implementation. It just calls the visit node, and it calls the nVisit node. Uh, I know sounds very complicated, and that's why I want to talk about an actual example and maybe like walk you through what's going on. This is the example in here. So we defined a new visitor called the visit function definition. And what's happening here is that you start with this one, which is the counter, and then you are basically telling it, okay, you start at the top, you visit each children, but the moment you visit the function definition, I want you to do this thing. And it's not even the moment you visit the function definition. The moment you return in the backward step, I want to do this thing. So it tries to like visit each of the node, and it tries to come back. And the moment it sees a function definition, it tries to push the name to a different structure, which is mutable, so you can just keep pushing into it. So what happens here is that, okay, function definition, these are the different, function definition nodes. Let me try to figure out the name of it. Where is the name? Node type function, src, visibility is public, it's non-payable. Okay, where is the actual name? Okay, kind, yeah, there you go, the name is right there. It's called set number. And the next one, which one is it? The next one is called increment. The next one is called set number. So these are two different data structures. One defines how each node will visit its children. The other one is a visitor, which has an override for each of the node. So it's like two different things, and they work together to create this thing called visitor pattern. And it just, tries to go like a yin and yang pattern where, the visitor goes to the node comes back to the visitor for the children, and then it goes back to the node, and then, this is this complicated diagram over here. And I think the only way to truly understand it is to write some code. I gave an example here of a visitor that would collect the names of the function. And I want you to write some kind of compiler using this idea to this programming language called dot. So let me try to pull up. What is dot. It's a very simple language to write to create graphs. So okay, it has a simple language like this, but you can build a graph like this. Okay, you have a node called A, and then you have a node called B, you have a node called C, and then there is an arrow you can draw from A to B, and then this can be compiled into a graph using this software called Graphis. So if you want a challenge, I would recommend you to create a Solidity AST to a graph or a dot compiler, which would take every contract, and it will draw like arrows to the function. So you can build a visitor which would override the contracts and also the function, and it would like draw the arrows from the contract to the function. I gave you a lot of hints. It's a little bit complicated to just understand by reading. You have to build something, and I already gave you a challenge to build. I'm just happy to help along if anyone has any questions while building it. And yeah, that's about it with the challenge.
Nice, interesting challenge. If I had more time, I would try it myself. But yeah, for anyone listening to this is definitely fun to do. Uh, yeah, you want to say something?
Yeah, I mean, if you wanna hack on it, you can just try to fork my repository. You can just try to I have most of the infrastructure built here, and you can try to hack around this basic.rs test and try to build this dot compiler. And then once you have this, once it compiles down to dot, you can use the command line interface for dot, and then you can generate this beautiful graph corresponding to your Solidity contract. And if you have seen any of this software that tries to build a graph out of the Solidity code, this is exactly how it does it. Maybe they're not trying to be as complicated as building visitors, but you have to effectively build a compiler from Solidity all the way to dot, and then the dot compiler would create this beautiful PNG or SVG that you can show somewhere.
Nice, nice. Yeah, that would be awesome. This would be a really cool thing to build. Anyway, listen, man, this was a super interesting discussion. We learned a ton. Um, I'm gonna put in the Solidity compiler, obviously, your repository and description bar down below. The one web page as well. If you could send me that, where it
For
shows
sure.
all the node types. Um, yeah, thanks, man. This was fun. Thanks for taking the time.
Amazing. Yeah, I also enjoyed talking about it. I always wanted to like give an overview of how the compiler works because there isn't a lot of advanced resources on how compilers work. I mean, there is some, but there is not a lot of practical discussions on how a compiler like Solidity is built. So I'm always happy to chat about how Solidity compiler works, how compilers work broadly, and some of the challenges you have to face, and all the trade-offs you have to make throughout building a compiler. So very excited to very I mean I'm very happy that I got some time to talk about it. But if anyone is watching this and want to learn more, like feel free to reach out to me on Twitter or somewhere else. I'm happy to send over some links or some ideas on what to work on.
Awesome. Yeah, I'm gonna link Harry's Twitter and GitHub in the description down below. And, we'll definitely do a part two. We have to. This was awesome. Awesome, guys.
Amazing. All right then.
Thanks,
Bye bye.
Harry, and thanks, guys, for tuning in.